Hello.
Sorry for that. Somehow it got disconnected. Just give me 1 minute. I'm trying to share my iPad. So, is there a way in which we can pin this and unpin this? Okay, now it is fine. Okay. Hello all. Sorry for a technical glitch here and there. So welcome to this live session on the third week of syllabus. I presume that I'm clearly audible and then my screen, my face, everything is visible. So text open here. So now what is that? So we are trying to do today. Okay. In today's session, now what I have planned is I will give you a non-mathematical overview of first 3 weeks syllabus. Now, what do I mean by that? Now, that doesn't mean to say that I'll not be showing you equations. No, I'll be showing you equations, but I'll not be taking you through the derivation. Okay. Now I'll be showing you. Okay, now this is how the structure is. Now this is how the loss formulation is. Now this is how you train, and this is how you update and infer. Okay. Now that will be the what do you call the structure that I overall have for today's discussion. And I presume that you all of you have gone through the syllabus that is there for 3 weeks, and then you're quite comfortable with the notions. Okay. Now, when I say generation, okay, now you know what does it mean. All those things, I presume that you are quite comfortable with. Okay. So, a vanilla GAN that we have, now we'll have two neural networks that we shall be implementing. Now, one is our generator, the other is the discriminator, or in terms of classifier guidance. Now, if you have understood it, now it is the binary classifier that we use. Now, the idea is now we sample from a normal distribution, and then uh, the neural network is converting this into x hat. And the idea is this x hat is from a distribution p theta, now wherein which this p theta and the data distribution px are close by. Okay, now this is the idea of generator. And then your discriminator is designed in such a way that now you give p theta or okay, now you give x hat from p theta, and then you give x from px. Now it should not be able to distinguish. It should not be able to distinguish. Okay. So now what does that mean actually? Now, if the discriminator is not able to distinguish between the real data and the fake data, what does that mean? That means that your generation is good. Okay. Now, your generation is good. Now, that is what we want. Okay. This is the structure that we have. Now, if we implement now this generator now using an MLP, now that is what we preferably call it as a vanilla GAN. And then if we implement it using a deep convolutional network, now preferably using a transposed convolutions, now this is what we call it as a DC GAN. Okay, deep convolution GAN or DC GAN. Okay, so I presume that you have implemented all of this or looked at the implementations now via tutorials. Fine. And now this is the loss function that we have. I will not be going into the derivation of this loss function. Now here d of omega or dw, now whatever you say, now this here now here omega are the parameters. Okay. So and then now this is the expectation. Now you can see here that from which distribution are you getting it? Now you are getting it from the px. Okay. Now this distribution is over px, the real data, and this is over the fake data or the generated data, which is from the distribution p theta. Okay, and this is your loss function. So now there is an expectation here. Now how do you remove this because no, we don't know the whole thing. Now how do you take care of it? Now we use law of large numbers, and then you can replace this expectation now using sample averages. Okay, now that is what we have done now, wherein which from the real data, now this is from the real data, as you can see here, this is just xi, this is from the real data. Now you have taken b1 examples, and then you're calculating the sample average, and similarly here you are taking it. Okay, now here you are taking it xj hat, which is nothing but the generated. Now how do you generate it? Now this generation is nothing but g theta of zj. Okay, now this generation is nothing but g theta of zj. Now this which is there now will get replaced by g theta of zj. Now what does this mean? Now this second term has both omega as well as theta. Okay, but the first term that you have is having only omega. Okay, now this is all your overall loss function that you have. Okay, so now that means that your first term that you have is independent of theta. Okay, this immediately now whenever you look at the equation, now you should be able to see this. Okay, now fine. Now this is your real data now which is from px, and this is your generated data which is from p theta. Now this is your gradient ascent step. Now you know why we are doing the ascent now, because you have an R max here with respect to W. Okay. Now if you want to do it with respect to theta, now as I told you, the first term is independent of theta, so you don't need to worry about the first term. Now you just need to worry about the second term. Okay. Now this is how you learn the parameters. Okay. So now how do you train it now? Let's look at the training procedure now. The training procedure goes like this. Now first you are trying to train the discriminator. Now whenever you are trying to train the discriminator, this is the discriminator and this is the generator. Fine. Now this generate for discriminator also, now if you see the discriminator, now this has theta inside it. That means that there is a parameter that needs to be taken care. Now because of which what we are doing, now if we keep on changing it, we keep theta as a constant while taking care of the discriminator. Okay. So now you take care of this. You obtain this is your loss function or the objective function. You obtain this function. Okay. And then you update only parameters till here. Now, because what is the parameter you're updating the discriminator parameter now, which is omega. Now that means that you will be updating only till here. Now, how do you do it? First, sample examples from normal distribution here. For sample from here, then pass it through generator. Now, once you pass it through generator, you get these fake examples. Okay. Now, then you pass it to the second term. Now, because of which you get this, the second value you will get. Now, similarly, you take B1 examples and pass it through just the discriminator, you get this term. Okay. Sample from the real data, obtain this term. Sample from the normal distribution, pass it through the generator, obtain the fake data, and get the second term. So now you have obtained this and this. Fine. So now you can take the gradients. You update the gradients. Okay, now you have got the loss function. With respect to that loss function, you obtain the gradients only till here. Okay, you will not be going further. You'll be only updating till here. Okay, so now then how do you train the generator network? Now that is, how do you obtain theta parameters? Is the question. Fine. Now if you look at the theta, if you look at this, the first term that is there is independent of theta. So that means that you should be only taking care of the second term. Now second term, you have to pass through omega. Okay. That means that like we kept theta as constant. Now whenever we are training the generator, we'll be keeping omega as constant. We will not be updating these weights. We'll be keeping these as constants. We'll pass the gradients here, and then we only update the generator parameters. Okay. Now you sample from normal distribution and then obtain the fake data and obtain the second term, and you compute the second term. And then what do? You pass the gradients like this, but what do? You keep the parameters of discriminator constant. Now this is how you perform the training. Okay. Now, but one thing should be clear. Now, we don't want discriminator to perform well actually. What do I mean by that? Now, whenever I give the real data and the generated data, now it should not be able to distinguish. Now, because of which, what I should do is, now I should not train my discriminator more. I should be training my generator more. Training in the sense, the updation of parameters should be happening for generator more. Okay. Now, how do I achieve it? Now, very simple. Now, you train generator for more number of steps compared to the discriminator. Okay. Because of which you will be able to get good quality of images. This is the idea of vanilla GAN. Okay. So any questions till here? If you have got any questions, you can ask me or put it in the chat. Anything is fine. Okay. So good. No question is a good outcome. So now the next idea now that you have is, now you can interpret now this GAN as a classifier guided generator mode, which makes total sense. Okay. Now from our basic understanding itself, yes. Now can the discriminator that you have be used for making P theta and P closer? Okay. Now that is the question. Yes. Now we have seen that. Now we have to tweak them with taking into consideration. Okay. So now, hence the classifier has to be simultaneously activated with the generator. No, that is what we are trying to achieve. And then the same idea now you can uh, get it from the previous discussion also. And then if you formulate it, now finally you get the outcome which is same as that of the vanilla GAN. Okay. Now whether you look at from the VDM perspective or from the classifier grade perspective, now you obtain the same what do you call outcome. Okay. Now this is full of uh, mathematical understanding. So I'm not going into it. So yeah. So the next idea that we have is DC GAN. Okay. Now in DC GAN, what did we do? Now, as I told you earlier, now the idea of DC GAN is okay. Now why to use MLP? Okay. Now rather than using MLP, now what we will use? We use an idea called as the transposed convolution layers. Now using the transposed convolution layers, we will be performing the upsampling. Okay. Now why is this? Now because the data size that we have, now because D that is there is typically quite larger than the size of Z. Okay. Now Z will be in the size of K, but X will be in the size of D. Now you have to upsample it. Okay. Now because of which we use something called as up convolution or transposed convolutions for generating. Okay. Now it is just a architectural tweak that we have done even during the implementation. Now, then comes the idea of conditional GAN. Now, why is this conditional GAN needed? Now, let's go back to vanilla GAN. If you look at the formulation, okay, now you don't have control over what category of images are getting generated. Now, you actually have no control over it. Okay. Yes. Now you can say that okay. Now at randomly many different classes of images can get generated. Yes, we have seen it, but you don't have control. Now, for example, I say that okay, now generate me images of class 3. I don't have control over it. Now, if I say that generate me 1,000 images of class 3, I don't have control over it. So now what do I do for it? Now, can I include this in my GAN training is the question. Okay. Now, this is the next question that we will ask. As it turns out, yes, that is the next idea that we shall be looking into is what is called as a conditional GAN. Now, the idea is pretty much simple here. Now, rather than just giving X as input, now, in addition to that, we give Y also as input. Okay. That's all is the idea. So now let's see how it works. Now you have your data, which is from a joint distribution Pxy. So now objective is to sample from a conditional distribution P of xy instead of Px. I will be giving you y. Okay. Now given y, now generate me an example. Okay. So now how is it? Idea is simple. Estimate P of x given y and make P theta approach Pxy for all y. That's all. Okay. So now what we used to do, now we used to see that now Px and P theta, now we want to be them closer. Now rather than that, what I'll do, I want P of x given y to be closer to P theta, not only for one y, for all y actually. That is the idea. Now this is the case. Now modify the generator and discriminator operate on conditional distribution. Now how do I do it? The idea is pretty much simple. Now, rather than just giving z, what I'll do, I'll give y also as an input. Now, how I will give y? Now, I will be giving it as one hot encoding. And then I expect that it gets from p theta of x given y. Okay. Now this is how I modify the structure of generator. Now similarly, what I'll do, I'll modify the generator. I'll modify the structure of discriminator also. Now I was giving p theta and px. Now what I will do, I'll give p theta of x given y and p of x given y, which is the conditional distribution. Now, with respect to y all, and I'll be giving y also in terms of encoding, and then it should be saying 0 or 1. It remains the same. So now your overall loss function or the objective function which is there, yes, now it should be considering the joint. Okay, you will be giving x and y also. Now here also you should be giving x and y. Okay, this is the idea of the conditional GAN. So any questions on, and everything just follows. Okay, everything just follows. So you don't need to worry about any other thing. Everything whatever we have discussed up till now just follows even with the conditional GAN. Any questions on any of the previous topics that we have covered? Yes, Satiki, go ahead.
Good evening, sir. Sir, I'm not pretty sure if I would be properly able to structure the question. So, pardon me if I'm
Sure, sure.
going wrong. Sir, so like I was studying a little bit about conditional GANs today. And so, sir, basically, I mean, the fundamental thing is like if we take a very small example, it is like if there is a label given, then what is the probability of the distribution over data point x if the label is y, right, sir? Because it is px of y. So, sir, basically, I what I wanted to ask is, sir, like, does a conditional GAN learn just from one big distribution, or like it learns from more than one in order to
Okay. And
sampling?
what is one big distribution? No, okay.
Yes,
I got your question. For
right.
all y. Okay.
Yes, sir. Yes, sir. Exactly.
Yeah. For all y. It's not only for one y. No, if that is what you mean by a small distribution, for all y it is considered. Okay.
Okay, okay, yeah, exactly, sir. That is what I was going to ask. So, sir, like now we have considered for all y, sir. So, I mean, so, sir, how do we ensure that the px given y is actually learned properly? I
Oh,
mean,
see, now that is taken care, right? See here, that is
uh,
taken care in each of the cases, right? You will be
right,
given y, right?
right, right,
Now,
right,
because of which it has to do it.
right,
See,
right,
now for example, if I say
mm,
that, okay, now let's take a case. Now
right.
I will be giving z, and then I'll be giving 3 here.
Okay.
Let me see, give some z and 3 here. Now then
Mm-hmm.
it has to generate an image of 3, right? If it doesn't generate an image of 3, then what will happen? Your classifier now will be able to say that it is now here you are giving 3, again you
Mm,
will be giving 3, and then you will be giving an image now which will not be 3. Your classifier will be more stronger. It should not be able to detect that it is 3. Now that means that it should be 3, right?
right, right. Makes sense.
Now because
Right.
of which the distribution is in such a way that it is generating the image of 3.
Oh, okay. Okay. Makes sense.
Okay.
Understood.
Yeah.
And sir, one very generic question. I'm not sure if this is a correct question,
No,
but sir,
please don't
like,
have any of those things. You can ask me any questions pertaining to syllabus. Yeah.
okay, sir. So, sir, like, we have used one hot encoding in this scenario, sir. So,
Mhm.
like, sir, how does this like one hot encoding of the label space affect the training stability, sir?
Uh, Very good question. See, uh, it will have issues. Okay, that is the reason why, as we go along, we will remove this one hot encoding, and then we do some other kind of encoding, which we will see sometime later. That's actually a good question. Yes. No, because your question is no, you suddenly have 0 1 0. You have something like this.
Right. Right.
Okay, you suddenly have something like this, and you don't know how is it working. Now, is this embedding good in any case? Now, that should be
Right.
the basic question. in your argument, the basic question is now how do I know that this embedding is good?
Right, sir, because there is no other reference point for me at this
Yes.
moment, sir.
So
Right, right.
now one way of saying it is, now since this my training, once it gets stabilized, now I'm not able to discriminate. Okay. Now that means that my encoding has to be correct.
Right.
Okay.
Okay.
That is
Okay.
one way of saying it. Another way of saying it is, okay, now is there any other kind of embeddings that we can do?
Mm-hmm. Mm-hmm.
Okay. Now for that, now we will have answer sometime later.
Okay. Okay. Understood. Thank you, sir.
Is any other questions? Is versus train again part of week 3 or not? I don't know. I don't remember. Let me look into it just a minute. I don't remember whether versus train GAN is
No, sir. I think in week 3 we just have inference till inferences. I
till
mean,
inference. Okay.
yes, sir.
Yeah, we don't have versus train GAN, right?
I said like as far as I remember, I'm not.
Yeah, yeah, let me go
I'm
through it. Yeah.
yeah, yes.
My memory is
It's
also
in week four. Week four.
V4. Okay. Thank you for that. Yeah. No, no. This is the overall idea till week 3. No, the idea is not to give you an umbrella picture. No, okay, what is that you're trying to do in till week 3? Okay. Now the idea is, no, you want to generate new data. Okay. So now, uh, okay. Now I'll give you a reference for this. I I recently saw a movie now called as My Fair Lady. It's a pretty old movie. Now, My Fair Lady is exactly like this. So now there the question arises is, now how do you differentiate a person to be a lady in the sense? So in the what do you call during the time of British era in England, there used to be people called as dukes and duchess, something like that, right? Now how do you identify a random person as an elite or not? Okay. So now the idea is, now if they speak well, now then you are able to. So now a phonetic person comes in and then she takes a lady from the street and then he will train her. Now finally you are not able to discriminate. Now that means that your training procedure is good. Exactly same idea, right? Now if the discriminator is not able to discriminate, now that means that you have done well. Your generation is correct. Okay. This is the idea of the overall uh, GAN that you have. I presume that that gives you an umbrella overview of what you have been looking. Now, if you got any specific technical questions, any derivations that you are stuck in till now, you can let me know. I'll surely answer that question.
Sir, just again out of curiosity, like here we are like as of now we are only limiting ourselves with 0 and 1 classification, right, sir? So, sir, like I guess there could be like I'm just asking, sir, because I don't know. Like, is there any like down the line are we going to study something which is related to multi-class?
See, okay. So
Yeah.
think of it like, now what is the aim of that discriminator? The aim of the discriminator is to say that whether the given image is real or not.
Right.
No, it is
Right.
not to classify the image into its groups. For
Ah.
example, if you
Okay.
are taking a MNIST data, no, you want to put it into buckets, right? No, 0 to 9 buckets you want to put it. No, that is not the aim of the discriminator here. No, please
Right.
don't put the idea of classifier into discriminator. The aim of discriminator
Mm.
is, no, I give you the generated image, I'll give you the real image. Now you should not be able to distinguish. Now, what do you mean by you should not be able to distinguish? My generation is so good that now the discriminator fails to distinguish.
Right. Right.
Okay. Now this is not the standard classifier that you have. In the standard classifier, no, we want to classify it we want to
Right.
classify it into certain buckets. Now here the discriminator should not be able to classify into the real and the fake buckets.
Right. Right. Right.
No, does that clears the idea of why are
Right.
we using a binary classifier here?
Yeah. 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 Makes sense. Makes
So,
sense.
are there degrees to how much it discriminates?
Okay, now the degree in the sense, now I prefer to give it in a different answer. Now, if you remember, okay, I don't know whether so where is the FID scores is somewhere down the line. Now we have a way of saying that now whether my generation is good or not. Now your question is now can I quantize? Now can I measure my generation goodness, correctness? Yes, as it turns out,
Yeah.
we have an idea called as FID scores. Okay, now it will come down the line. Now in the coming weeks, there is something called as FID scores, using which now you will be able to what do you call measure the goodness of generation. Okay, and we have even coded that FID scores that you can take it as a generic thing, and then you can compare your generation across the different implementations that we have. Make sense? Any other questions?
Is this just one last
Go ahead,
question,
go
sir?
ahead.
I
No,
wanted.
no, go ahead.
Sir, like since it was meant, like explicitly mentioned in the lecture that sir, if p of x and p of theta are equal, then the classifier is going to fail. But it is not the other way around. The classifier failing doesn't necessarily mean that these two distributions are equal, right, sir? So in that scenario, sir, just out of curiosity, I wanted to ask, like, could there be like what is the like what could be the condition that the discriminator fails, but px and p theta are not equal? uh, I mean, they are not equal to each other. So like what could be some generic properties in that scenario?
Which lecture was it?
Sir, this one, the classifier thing, sir.
Classifier.
Yes, sir. Yes, sir. I think it is at the very beginning, sir, where the diagram was made, sir.
This diagram.
Yes, sir. Where, yeah, I think it was there only in the counter example.
See, now, the idea of this diagram is
Right.
not that. Okay. The idea of
Okay.
diagram is something different. So
Hmm.
now this line is your discriminator.
Right.
Okay. Now this is your data px.
Right.
Okay. Now consider that you come up with this line.
Hmm. Right.
Okay. Now, okay. Now this is okay. Now there is some labeling mistake here. Now if this is the line, it is able to distinguish properly.
Right.
Is that what we want? We want the discriminator to be like this. If this is the real data and this is the generated data,
Hmm.
now do we want the discriminator like this?
No.
No, right? No,
No.
because it is able to distinguish.
Right.
Okay, no, we don't
Right.
want it. So
Right.
you train. Now, because of which, what will happen? Now so whenever you change the parameters of W, no, that means that you are changing the line.
Hmm. Right.
Whenever
Right.
you are
Yeah.
changing the parameters of theta, you are changing this cluster.
Hmm. Hmm.
So
Hmm.
now,
Hmm.
if you change the cluster and do it, now then what will happen? You will go here. Is this doing like that? You can keep on toggling.
Oh, okay. Okay.
Ah,
Okay.
that is what is being said.
Okay, okay. So it's like it's sort of hit and try, sir. Okay, okay.
So this is a saddle point problem. Now these are some of the problems that are there. Okay. There is a
Mm-hmm.
so as you can see here, there is a possibility that p theta can toggle between p theta 1 and p theta 2 alternatively. Theta 1. So
Mm-hmm.
what you will do now, if you get here, I'll move here. If you get here, I'll move here.
Right, right, right.
This is an issue.
So like there, like you were mentioning the tweaking part. Does the tweaking part come there once?
Speaking of what?
So the tweaking of theta parameters of.
So that is what training is, right? Now, training.
Mm-hmm.
So whenever you are performing the training, you're always tweaking the parameters, no?
Right, right.
Now, because of which there will be movement like this.
Okay,
Okay.
understood. Understood. Thank you.
So okay, now what you are saying is, however, failure of the classifier doesn't imply the distributions are matching. Okay. Now what do I mean by that? You have data here. Okay. Now I got your question. Now you have the data here, and then you have the data here. Okay. Now this is your real. This is your generated. Now if you have a line like this, now are you able to distinguish now?
No.
No, but you are not able to
Hmm.
distinguish. But
Hmm.
does that mean that p theta,
Ah,
these two are same?
understood. Yes, sir. Understood your point.
Now
Yeah,
got it.
yeah, 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 yeah,
Ah,
yeah. Okay.
just because your classifier is not able to distinguish, that doesn't mean to say that the distributions are matching.
Right, right, sir. Right.
Any other? So you guys implemented generated images. Are they looking comfortable? Tried anything? Tried anything different? Have you tried these different one step through the discriminator, one step through the generator, one step through the discriminator, five step through generator? Like this, have you tried implementing these things? Was the generations good?
I'm yet to try, sir.
Yet to try. Okay.
Right.
Now I presume that all of you have got the link for my GitHub repository, in
No,
which
sir.
okay,
No.
I think it will be shared. I think it will be shared. No need to worry. So when which all the collab notebooks have been put into one place, you can make use of it. Yeah.
So global optimum P theta becomes equal to Px, right?
Yes. It's a saddle point problem. Yes. It's not global optimum. I don't know whether to call it as global optimum or not.
So
It's
there
a
was a
saddle.
question on this. I got it wrong actually.
Which question?
So there was a question on this one in the graded assignment.
Okay. What was the question?
I'll
Sorry, I
share
don't.
my
I
screen, sir.
don't know. No, you cannot share. You can just put your question in the chat.
Okay, sir.
Which weeks?
So it's week 2 actually.
Week two. Which question? Question
So
number?
question 9.
No. The original GAN objective is. Is that the question?
Yes, sir. Yes, sir. Original GAN objective, min max
No.
form.
Yeah, that is. Yeah, you are able to get it right? No?
So I got it like I got this one wrong. It's like I marked total value 0, but then I think I got it.
Okay, so now think of it like this. Okay. Now you're for real image, consider this as the one hot encoding. For generated image, consider this as one hot encoding, and find the second thing. Okay. Now you'll be able to get it.
Okay, sir.
Just give it a try. It's a fairly straightforward question. If you're not able to do it, let me know. I'll surely explain you the answer.
So could you just Redo, what did you say? Z10 0.
See, real image, let the thing be this. Let the one hot be this.
Hmm.
For fake, let the one hot be
Okay.
this. Then what happens to the discriminator loss in this case? Just think of it.
Loss here would be sigmoid, right?
Okay, do it. There is some more tweaking that is needed. Oh, yeah, the answer is on your screen also. But anyhow, that also we can try from the next live session. What I'll do is I'll even solve the previous questions that were asked in what do you call grade assignments. Also, we can even try that so that it will give you much more comfortability on these ideas. That we will try from next session. Yeah, the reason is no. First, I have to write it down. Okay. Now, sometimes I'll be having some kind of intuitive way of understanding it. Now, I should derive it the way in which it is needed for a session. Okay. I'll do it, and then from next session, now for all the 4 weeks, now we will sit and do it, so that no, you will have a better understanding. We will do it. Now, any additional thing, no, you need. Okay. Now, please let me know. No, we will surely implement it. Okay. Now, if you feel that okay, now you need much more implementational details, yeah, we will surely do it. Now, whatever information you need, whatever kind of assistance you need, now feel free. Now, we will surely provide it. Okay then. So, any other questions, guys? Please give it a try on implementing. Now, only when you implement, see again, I'll tell you now. If you look at any of my implementation tutorial, now what I'll be doing is each equation I'll be showing the equivalence with the code. Okay, now that please do it. Look at it. Now that will give you a fairly a nice idea of okay. Now, if you get a problem, okay, or if you have an equation, how do you transfer that equation now into a code? Okay, now that will give you a fairly nice idea. Please do that. Okay, now I'll be always be toggling between my iPad's equations and then the implementation that I show. Okay, now because of which now you should be able to get a fairly nice idea of okay, now this is a mathematical equation and how is that equation translated into a program. Okay, so is anybody from team is here? Can we wind up? Do we have anything else? Okay, sure. Thank you. So thank you, guys. We will wind it up for this week. From next week, what we will do is we will even solve the graded solutions. We will give a detailed solutions even for that. If you need anything else, please let us know. We will implement that also, and then we will see to it that you understand what we are trying to teach. Okay, then. I hope you are having good time now learning how mathematics is so important and how mathematics translates to programming. I assume that you are learning it. Sure. Okay,
Much
then.
better than the framework, sir.
Much
This
better
part,
than.
so this part is much more interesting than actually using the framework. I mean the like this part is more interesting than using
Yes.
Gen AI.
Yeah. Now, if you just perform an API call, you don't see what is happening in
Exactly,
between. Okay.
exactly,
Now,
exactly.
that is more exciting. No, no,
Right.
no. That will open up the ideas for okay. So now, what might be if I face a similar situation like this? You'll open up for ideas. Know what I can do later. Okay. No, those things no, will be an additional advantage. Okay. Yeah. Good that you guys are enjoying it. So let's meet next week. same time. Till then,
Uh,
bye bye.
Sir,
Good,
before
good, good.
sir wrapping up, I'm really sorry, sir. Since Devanshi was asking something about the optimum, global optimum thing,
Uh,
so in the lectures we saw that the discriminator and the generators are trained alternatively, right? So
yes,
for
yes.
this, so sir, like if we fix the generator, like is there any concept of any sort of like an optimal discriminator which can be derived?
What do you mean by optimal discriminator? Is the one which should not be able to classify.
Ah, okay, okay.
That is the idea, right? Optimal discriminator is the one which should not be able to classify.
Right, right, right. Yeah, yeah, makes sense. Yeah, 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 yeah. Okay,
Okay.
got it, got it.
Yeah. Good. Any other questions?
Not from my side, sir.
Not
Thank
from your side. Okay.
you. Yeah.
Okay then, guys. Bye bye. So let's meet next week.
Thank you, sir.
Thank you. Bye bye.